Analysis of recursive algorithms. So in the last class we have seen about the non-recursive mathematical analysis of non-recursive algorithms. So today we will be discussing about some of the algorithms, recursive algorithms, and we are going to find out the time efficiency of those algorithms. At the same time, we are going to establish the general plan to find out like the efficiency of the recursive algorithms. Okay, as a first example, let us take the algorithm to compute the factorial of a given number. So make sure that you are going to write a recursive algorithm. So what is a factorial of a given number? So if you are taking some n is equal to 3, how to find the factorial of 3? We know that 3 can be written as 2 factorial, and 2 factorial is nothing but 2 into 1 factorial. Okay, and we know that the factorial 1 is 1, so this is 2, and substitute this value here, so it will become 3 into 2, 6. Okay, so that means we can if you are finding factorial value, suppose factorial value of 3, so we can say that this can be written as 3 into, then find out the factorial of 2. Okay, and 3 into factorial of 2 is, we can write this as factorial 3 into 2 factorial of 1, and we know that this is the we know the value of factorial 1, that is 1. So 3 into 2 into 1, it becomes 6. Okay, so we can write the algorithm like algorithm, then f is the name of the factorial function, n is the number for which we are going to find out the algorithm. And compute, what is the description of the algorithm? Compute the value of n factorial, and the input is nothing but n, I'm writing in short, and the output is the value of n factorial. Okay, then if n is equal to 0 or 1, anything you can write, we know that we need to go write return 1. Otherwise, what we are going to write? So we are going to return f into n minus 1 multiplied by n. Okay, so what is meant by this? How? Let us see how this algorithm will be executed for the value n is equal to 3. Okay, so let us write algorithm, and the value of n is equal to 3. So if n is equal, 3 is equal to 0, okay, if n is equal to 0, 3 is equal to 0, no. So that means it comes here, return f of 2 multiplied by 3. So f of 2 is nothing but it is a function call. Again this f of 2, so algorithm f of 3, this one. So again it goes to the starting of this algorithm. Then algorithm, and now f of 2. So now we will be checking this, n is equal to 0, that means 2 is equal to 0, no. That means again it will be return f of 1 multiplied by n is equal to 2 now. Okay, again this is a function call, then it goes to the starting of the function again, that means algorithm f of 1. Okay, so if here f of 1 is equal to 0, no, then it becomes return f of 0 multiplied by 1. So again this is a function call, it goes to the starting of the function again, so algorithm f of 0. 0 is equal to 0, yes. So what will be the return value? Return 1. So that means return 1. Where this value will be returned from to the function call. Where is it called from? From here. So 1 will be substituted. 1 into 1, 1. So this 1 value will be returned to the calling function. That means that will be substituted here. This is 1 into 2. Then this is returned, it will be returned. 1 into 2 will be returned to the calling function. That means this is the 1. So 2 will be substituted here. So here 2 into 3, 6. This is the final value which will be returned to the calling function. Usually we will write main function as a calling function. So this is the function, recursive function for finding the factorial of a given number. Then how you are going to find out the efficiency of this algorithm? So what we are going to do is we are going to find out what is the input size indicator. So what is the input size here? The number n itself. Okay, and what is the basic operation we are performing here? We are comparing, but we are having a multiplication operation also. So usually the operation which takes more time, that we will take as a basic operation. So in this case we are finding this, we are putting this as a basic operation, that is a multiplication operation as a basic operation, Okay, and what we are going to do is we are going to write because it is recurring, that means it is occurring again and again. Okay, we are calling, if you see these instances, we are calling the same function again and again, but for the different values of n. So that means we are going to set up a recurrence relation for that. Okay, so what is that recurrence relation? F of n is equal to f of n minus 1 multiplied by 1. So that is what we have done here, right? So if this is n, so this is f of n minus 1 into this one. Okay, so that means now we are going to establish how many number of, because we have the basic operation as the multiplication operation. Now how many number of multiplication operations are going to be taking place? So m of n is equal to m of n minus 1 plus 1. What is meant by this? So this is, if it is a 1, if n is equal to 1 for this is number of multiplication is nothing but here to compute, this is nothing but to compute the values of f of n minus 1, and this is 1 is to multiply f of n minus 1 into n by n. Okay, this is when for n greater than 0. Okay, so this is the recurrence relation which we are going to keep, right? M of n is equal to m of n minus 1 plus 1. That means the time taken for the remaining n minus 1 plus the time to multiply this n, number, multiply this f of n minus 1 into n by n. Okay, so that means, let me show again. So n into the time taken for this n minus 1 and plus 1 is 1 multiplication to multiply whatever the value we are getting, that with n. So that's why we are writing like this, right? Okay, so this is the recurrence relations we are going to establish. So for that we should have initial conditions. Okay, so for every recursive functions we need to have the initial conditions or base conditions, otherwise it will go into infinite loop. What is the infinite condition? So what we have written in the function, we have written that if n is equal to 0, then return 1. So that means if n is equal to 0, return 1. This is the initial condition. So that means m of 0 is equal to 0. And also if only one multiplication, if there is n is equal to 0, then there are n number 0 number of multiplications needed. Okay, so then recurrence, how do you write the recurrence relation and initial conditions together? The recurrence relation is m of n is equal to m of n minus 1 plus 1 and m of 0 is equal to 0. Okay, then let us use the, if you remember in the beginning of the semester I had explained about the backward substitution. So we will be using the backward substitution. So by using the method of backward substitution, we are going to substitute this backwards. How? So m of n is equal to m of n minus 1 plus 1. So we are going to substitute the same for this. So that means m of n minus 1. So instead of m of n minus 1, so this is, instead of n, you are going to put n minus 1. So n minus 1 minus 1, and this plus 1. Plus 1, this is for this. And this is, okay, let me take like this. M of this n minus 1, okay, plus 1 plus 1. Okay, so this is nothing but m of n minus 2 plus 2. So now we are going to substitute n minus 2 instead of n. So that is m of n minus 2 minus 1 plus 1 plus 2. So that means it becomes m of n minus 3 plus 3. Okay, so how do we write the general form then? So general form will be m of n is equal to m of, so this is n minus, let us write the ith term. So that becomes n minus I plus I. Okay, now what is the initial condition? M of 0 is equal to m of 0 when n is equal to 0. So that means we can write this as m of n is equal to m of I mean, we have to make sure that, I mean, which value of this I makes m of 0. So that means we can take I is equal to n. Then it becomes n minus n plus n. Okay, so then m of 0 plus n, it becomes 0 plus n. It is equal to n. That means this belongs to theta of n. Okay. So this is the time complexity of the factorial, finding factorial of a given number. Then, so with this, what did we do in this? We have seen what is the input size indicator. Then after that, what is the basic operation? And after that, we had established the recurrence relation and also the initial condition. So by writing this recurrence relation and this one, we had we tried to solve, taking recurrence relation, we tried to solve the recurrence relation by using this initial condition. Okay, so this is by using the back substitution method, which we are already aware of. Okay, now let us come up with the general plan for analyzing the time efficiency of the recursive algorithm. So what is the first step we have done? So we had decide on a parameter which is indicating the input size, which is indicating the input size. Okay, then next, obviously, like whatever we have done for the non-recursive is the same thing. So that is identify the algorithm's basic operation. Okay, and next, check, and also we have to check whether it is dependent again on worst, average as well as the best cases or not. Otherwise, only one case will be taken into consideration. Next, what we are going to do, we are going to set up a recurrence relation, because this is the extra step in the recursive algorithms, whereas non-recursive algorithms we don't have this step. So set up a recurrence relation. Okay, then after that and also initial condition, with an initial condition. If the initial condition is not there, then it is very difficult to solve this recurrence relation. Okay, and this recurrence relation in regard of how many number of times the basic operation is executed. After that, you have to solve the recurrence relation. After that, the sixth step is establish the order of growth. That is theta of n or theta of n square or theta of n log n. So one of the orders of growth you have to establish. So this is the general plan for analyzing mathematical analysis of time efficiency of the recursion.